Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today, we are starting a new section by diving into series expansions. We'll be looking at what Taylor series are, so if you're ready to learn, then let's get into it. Let's consider, firstly, a function f of x where x is a single independent variable, where all of the derivatives of this function f are known at the point x0. So at this point, all derivatives of this function is known. Then, if we wanted to evaluate what is the value at this point, which is f of x0 plus h, how might we do that? Well, we could use a power series, and this would look like f of x0 plus h equaling a coefficient alpha 0 plus another coefficient alpha 1 times by h plus alpha 2 times by h squared plus the rest. And you could set this equal to just a summation sign of summing from n equals 0 to infinity of alpha n times h to the power of n. And we need to determine these coefficients, alpha n. So to calculate the first coefficient, alpha 0, we can set h equal to 0, and that gives us f of x0 only, which gives us our alpha 0 value is just f of x0. Then differentiate with respect to h, and we'll get that f prime of x0 plus h is equal to alpha 1 plus 2 alpha 2h plus 3 alpha 3h squared, etc. And so what we can do again is then set h equals 0, and we'll get that f prime of x0 is equal to alpha 1. And you might be able to see where I'm going with this, and you can take then the second derivative, and you'll get that alpha 2 is equal to f double prime of x0 divided by 2. That might not be too obvious immediately, but if you just look at this equation here, we'll see that differentiating with respect to h, we'll have just a 2 alpha 2 at the start, and that would be equal to our f double prime of x0 plus h. And then when we set all our h's to 0, remember we'd have differentiated this one away, we'll just have that alpha 2 times by 2 is equal to f double prime of x0, and so alpha 2 is f double prime of x0 divided by 2. And again, just to show, you could also get alpha 3 is equal to f triple prime of x0 over 3 times 2, which is 6, but you'll see why I've written 3 times 2. And so we can leave this to our general result, which is that alpha n is equal to f differentiated n times of x0. So like I said at the start, we know the derivative of f at the point x0. We know all the derivatives. And so this is a known value that we already have. And then we'd just divide that by n factorial. So you could view this as alpha 1 is actually f prime of x0 divided by 1 factorial, or that alpha 0 is over 0 factorial, which is 1. And you'll see that's just 2 factorial, so 3 times 2 times 1 is 3 factorial, etc. And you can see how we get this final result for our alpha n. And so what that gives us is the Taylor series. So for our function f of x, about the point x0, which is where we know all our derivatives, we get this Taylor series, which is that f of x0 plus h is equal to the sum from n equals 0 to infinity of our alpha n, which is f differentiated n times at the point x0, divided by n factorial times by h, which is our small increment to the power of n. So this is our Taylor series. An alternative expression for this is to write that f of x is equal to the sum from n equals 0 to infinity of f differentiated n times at x naught divided by n factorial, so that's the same, but we now have f of x instead of f of x naught plus h, and now we're just going to be timesing that by x being our new position minus x naught to the power of n. So you can imagine all we're doing there is just saying that x is x naught plus h and subbing that in. And so we can remove h and just use x as a general form. And this tends to be a more useful expression of the Taylor series. Note that this whole description here isn't actually a proof, a formal proof. It relies on various assumptions about, for example, differentiating an infinite series. And we'll see more about that in the next section of this functions topic, where we'll be looking at series and convergence. But for now, we can just consider the successive terms of the Taylor series as improvements to higher and higher order to a local polynomial approximation. So you could start with just a function value, then you can look at linear and then quadratic and cubic and so on, and it would get more and more accurate the more terms you add. Perhaps a unnecessary, but I think it's interesting way to look at this, and feel free to skip ahead to the next portion of the video, but if you want to have a sort of another way of seeing where this Taylor series might come from, we can look at, firstly, let's just say, if we look at this function here, and we say, okay, a and b both are points where the function is 0. So I should probably write that this is our y equals 0 or f equals 0 line. So there exists, therefore, if both of these points, a and b, and our function is a continuous and differentiable function, there must exist an epsilon between a and b where the gradient is 0. This could be any shape. It could be some weird, that's a multi-valued. If it was something like this, there was multiple points there where the gradient has to be equal 0. It could go as many times as you like between. At some point, it must be 0 because, and if all of the points were 0, then the gradient as well is 0. So we can say with certainty there's an epsilon between these two values a and b where the gradient of f of epsilon must equal 0. And you could look at this again, you could have more than one epsilon, like I was saying, one here and one here, where our gradient is 0. Therefore, what you can do is now look at just a general function. It doesn't have to have these points a and b which are 0, just any function. There must exist a point between a and b where our epsilon now provides the gradient of the chord between a and b, if that makes sense. So this is our chord from our points f of a to f of b, and between there you can see these gradients are going to be changing and changing until we get to our epsilon point, which is the same gradient as between a and b, this chord, and then we'll have changing gradients again. And like I said before, this again could be any sort of function. We had one there and one here that time, and I think one down there. So you can have multiple epsilons, but let's just take this simple example of just some curve. And so there's an epsilon between a and b such that the gradient of our function f at epsilon is equal to this mean value, or just simple difference gradient, where we've just minus the y values, minus the x values. You'll be used to this from GCSE, A-level, or whatever your examinations are in other countries. So having that, we can rearrange it and say, let's times that across and add the f of a to the other side, and we'll get that f of b is equal to f of a plus the derivative of f at epsilon times b minus a. Now, if we say, okay, b we just are going to call that x, and a we'll call x naught, then this looks very familiar. We're going to have f of x equaling f of x naught plus f prime of epsilon times x minus x naught. And it looks familiar because that is basically the first two terms of our Taylor series. You can imagine this first term is just going to be f of x naught, and then the second term is going to be f prime of epsilon times x minus x naught. That's when we get this term included in that second term of our Taylor series. We can extend this mean value theorem, I think is what this is called, which I won't show here, but you can see this does reproduce the Taylor series, which I thought is just quite a neat result. And if you want to look into that more, I think it's called the remainder theorem or Taylor's theorem using the first mean value theorem. Another word that covers Rolle's theorem. So looking at those words, I'm sure you'll find what I'm talking about. And yeah, so let's move on to an example. If we say f of x is equal to 1 plus x squared, and we want to know the Taylor series around the point x naught equaling 1, what we can do first is say, okay, what is just our derivative in terms of x? We'd have f prime of x equaling 2x, f double prime of x equaling 2, and then f triple prime of x is where our Taylor series will terminate or truncate, and that is equal to 0. And we know it will truncate there because it's equal to 0, if that wasn't clear. So if we write this out, we would have that f of x can be written as 2 times our x naught, which is 1, plus 2 times our x minus x naught, which is going to be x minus 1, plus 2 over 2 factorial times by x minus 1 squared, and then no more terms after that. So this is our Taylor series expansion of the function f of x equaling 1 plus x squared. So our next function will be f of x equaling sine x about the point x naught equaling pi over 4. Let's start in the same way. Let's say, what's our first derivative? So f prime of x, that's just going to be cos x. Then f double prime is going to be minus sine x. F triple prime will be minus cos x. And then we're back to the start again if we continue. So this one doesn't terminate. There's no f differentiated n times of x which equals 0. There's no point where that happens. It will just repeat forever. So what we can write is that our function f of x is equal to, well, the first term is going to be sine of x naught. So that's going to be 1 over root 2. And we'll have more terms, which you can see if you can add more to what I've written and try and decipher where I get these values from. So the next one will be 1 over root 2 times x minus pi over 4. And then the next one will be minus 1 over root 2 times x minus pi over 4 squared over 2 factorial. And then guess what the next one will be, and so on. And it does not terminate, like I said, but it performs well for small values of x minus pi over 4. So when x minus pi over 4, the size of that is small. Today we've learnt about Taylor series. In the next video we'll be looking at what Maclaurin series are. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.